I am Shreya Gupta and I am going to explain about direct and indirect band gap semiconductors using EK diagrams. First, let us see what is band gap. The energy difference between the highest occupied energy state of the valence band and the lowest unoccupied state of the conduction band is known as band gap, and it is indicative of the conductivity of a material. Semiconductors have a small band gap compared to non-metals, which allows them for a meaningful fraction of the valence electrons of the material to move into the conduction band given a certain amount of energy. In non-metals or semiconductors, valence band is the highest range of electron energies in which electrons are present, and the conduction band is the lowest range of vacant electronic states. Band gap of a semiconductors are of two types. First, direct band gap and indirect band gap. First, let us see the concept of crystal momentum or K vector. The minimal energy state in the conduction band and the maximal energy state in the valence band are characterized by crystal momentum K vector, where crystal momentum equals to h cross k, where h cross equals to h by 2 pi, where h is Planck's constant. In direct band gap, if the k vectors are k vectors for minimal energy state in the conduction band and the maximal energy state in the valence band are same, then it is known as direct band gap. For direct band gap, crystal momentum of electrons and holes is the same in both the conduction band and the valence band, so an electron can directly emit a photon. In indirect band gap semiconductor, the top of the valence band and the bottom of conduction band occurs at the same value of momentum. As we can see in the EK diagram for direct band gap, here maximum of valence band and minimum of conduction band occur at same value of momentum. Now let's move to indirect band gap. If the crystal momentum or K vectors are different, then it is called indirect band gap. In an indirect band gap, a photon cannot be emitted because the electron must pass through an intermediate state and transfer momentum to the crystal lattice. For indirect band gap semiconductors, the conduction band minimum and valence band minimum energy levels occur at different values of momentum, as we can see in the EK diagram for indirect band gap. EK diagram or energy momentum diagram. Here maximum of valence band occurs at a momentum less than the momentum at which least of conduction band occurs. Now let us discuss the recombination in direct and indirect band gap. To shift an electron from the highest energy state in the valence band to the lowest energy state in the conduction band in direct band gap semiconductors, momentum required is very less or negligible. A photon of energy Eg, where Eg is band gap energy, can produce an electron hole pair in direct band gap semiconductors quite easily because the electrons does not need to be given very much momentum. While in indirect semiconductors, an electron cannot shift from the highest energy state in the valence band to the lowest energy state in the conduction band without a significant change in momentum. So to produce an electron hole pair in an indirect band gap semiconductor, electron needs to interact not only with the photon to gain energy but also with the lattice vibration called a phonon in order to either gain or lose momentum. So now compare the direct process and indirect process. Direct process is when direct band gap is involved, and indirect process is when indirect band gap semiconductors are involved. In indirect process proceeds at a much slower rate as it requires three entities to intersect in order to proceed: an electron, a photon and a phonon. This is analogous to chemical reactions, where in a particular reaction step a reaction between two molecules will proceed at a much greater rate than a process which involves three molecules. The same principle applies to recombination of electrons and holes to produce photons. The recombination process is much more efficient for a direct bandgap semiconductor than for an indirect bandgap semiconductor, where the process must be mediated by a phonon. Also, in direct processes, probability of recombination is higher than the probability of recombination in indirect processes. So the efficiency factor of a direct bandgap semiconductor is higher than the efficiency factor of an indirect bandgap semiconductor. Now let us see what are the uses of indirect and direct bandgap semiconductors. As a result of consideration which we discussed above, gallium arsenide and other direct bandgap semiconductors are used to make optical devices such as LEDs and semiconductor lasers, whereas silicon, which is an indirect bandgap semiconductor, cannot be used for such purposes. Thank you.